our machine learning class. And today we are going to discuss a very important topic on assembly. So we have split it into two parts. Today we are going to discuss the definition, the basic mathematical intuition, and then some types of ensembler. Also, we'll look at random forest and bagging in little bit more detail. Okay, so as I discussed, so here is the content. We'll discuss about the definition and basic idea, and then we'll look at types of ensemble with focus on random forest and bagging. Okay, now uh, let's understand that what is the philosophy of ensemble. So many cases what happens is that you are not sure about, so it's a new kind of, it's a new kind of disease. Okay, so then what happens is that you, when you go to a doctor, uh, you are not sure about it, right? So you take another opinion, and then you will take several opinions, right? And then probably you say that what majority of the doctors are saying. Okay, and it is very commonsensical that what majority will think probably will be right. Okay, so that's what is conceptualized in ensemble. So here of course we don't have doctors, but we have experts, and our experts are our classifiers. So what we'll do that using the training data, I will train multiple classifiers. So here is my training data. Okay, and I am using multiple classifiers uh, who are being trained on this training data. All right, now once the training is done, how the decision will be made. Okay, so the most simple scheme is that if there is a new instance, maybe this classifier is saying the class level to be 1, this to be 1, this to be 2, and this classifier to be 1. So majority are saying to be 1. So ensemble's prediction using majority vote will be 1. Can we use this for regression? Of course. So in that case, we will take simple averaging of the regression model's prediction. Now what we call such kind of vote? We call such kind of vote as hard votes. Okay. But now one question that come to your mind is that, okay, this is fine. So we are bringing a lot of classifiers, and of course, which is more coding, right? More CPU consumption. So is it worth it? Why should I do it? I mean, will it really work? So let's look at an example. The scenario is like this, that you have multiple classifiers, and all of the classifiers have accuracy of 70%. So you have three classifiers who has accuracy of 70%. Okay. Now let's see how it works. So how do I find out the probability of the case where all classifiers are correct? So you can think of this as a joint probability, right? All of them are correct. And as they are independent of each other, okay, or let's assume as they are independent. So it will be simply multiplication of probability of A being correct, probability of B being correct, and probability of C being correct, where A, B, and C are your classifiers. So you may say, okay, then my accuracy is going down where all are getting correct. But hold on, we talked about majority voting. So the case where two are correct and one is incorrect, so this will also be a case where the prediction will be right. So essentially this is combination of three events which are disjoint. Okay, so first case is that the third model goes wrong, the second case is that the second model goes wrong, and the third case is that the first model goes wrong. So we calculate the probability by using this independent log by 1. So we can do 0.7 into 0.7 into 0.3 three times, and we get it to be 0.4409. So approximately 44.09%. Here itself we can see that we are already at 78% correctness. However, rest of the two cases do not add to the accuracy. So in one case only one will be correct. Okay, so similarly we have found the probability, and we see that it has a probability of 18.9%. And case 4, none of them are correct. So that happens 2.7% of the times. But however, we can understand that if we use three classifiers and combine them, from 70% it goes up to 78% or 78.3%. Interestingly, if we increase number of classifiers, it will go further up. So we have checked the figures for 3, 5 and 7, and here is the graph, right? So for 1 it is 70, for 2 it is 78.3, for 3 it is 83.6, and for 7 it is 87.4. Okay, so this is how it is rising. Okay, so that is the intuition why we are going to combine it, right? Now your question might be that if that is the case, so is it always if we combine, then our accuracy will be improved? So one of the things what we did in this calculation is we multiplied when we tried to find joint probability. That is, probability of A and B we found that as probability of A into B. Okay, so this happens only when they are independent. So classifiers, when they are independent, you can say that they are uncorrelated. So let's look at an example. So here what is happening is that this 1 and 0 basically indicates that where the classifier is correct, it is 1, and where it is not correct, it is 0. Okay. So C1 has a classification accuracy of 80%. C2, if you follow its prediction, is completely same. So that means that these two classifiers are completely correlated. And C3 is also quite correlated. Only this observation it has a wrong value. And see what happens. If you ensemble, you end up getting 80% only, right? You don't get more than that. So why is this happening? Because they are completely correlated. Now let's see a case where they are not that correlated. So here if you see the first one and second one and third one, they are quite less correlated. C1 has an accuracy of 80%, C2 has an accuracy of 70%, and C3 has an accuracy of 60%. The ensemble whereas gives us 90% accuracy. So this was a case where they were correlated, it didn't increase at all, and here one of the classifiers had such bad accuracy like 60%, but the overall classification accuracy has increased to 90%. Okay, so the key is that we have to pick up uncorrelated classifiers. Okay. So apart from that, apart from increasing the accuracy when the classifiers are uncorrelated, it makes the decision boundaries quite robust also. So if you see that this was one classification boundary, so which was probably closer to this negative class, this was one where it was closer to the positive class, and this one was little bit very bumpy, right? Whereas if you combine these three classifiers, then the decision boundary that you get maybe is this blue line, which separates these classes well. So this you do not find by classification accuracy, but actually your robustness increases. Okay. Now let's look at the concept of hard voting versus soft voting. So the way that we discussed is that we'll look at majority vote. Is there another way? Okay. So here, this is a hard voting scheme. So classifier 1 has said C1, classifier 2 has said C2, classifier 3 has got C3. If we want to use soft voting, please understand the output of the classifier needs to be a probability distribution. Probability distribution meaning that it will assign a probability of, or assign a probability to each class. Okay, so that sum will be 1, but it will rather than a hard coded value, it will give you a probability. So let's look at an example. So same thing, classifier 1 has set the probability to be 0.51 and 0.49. That's why it has predicted to be C1. Classifier 2 has assigned 0.2 to C1 and 0.8 to C2, and classifier 3 assigns 0.52 to C1 and 0.42 to C2. Okay. So now if you sum them up and take an average, you will say no, the confidence for class 2 is more. Okay. So it will go for class 2. So that is what is the difference between hard voting and soft voting. And in most practical cases, when you use soft voting, your accuracy increases. Okay. So here what we were doing were, for prediction, we were using a weight. Okay. Now, instead of prediction using that as like that, what we can do is we can use the expertise or the competence of each of the classifiers. So we find the support for each class, okay? Support for each class for each classifier. And we multiply when the decision comes out, we multiply the decision by the support, okay? So only when a classifier has a good support, his decision will be weighted more, right? So that is also very commonsensical, okay? Now let's come to bagging. So bagging, this name comes from Bootstrap aggregator, okay? So for time being, let's just assume that Bootstrap sampling is a type of sampling. So what we are doing is, we are doing a sampling and creating different subsets from the original subset. And then we are training different models on each one of them, okay? And finally, when the forecast is coming, we are combining or aggregating the result, okay? So this is a very, very simple concept which is, found in bagging. Now, of course, one question will be that what is this Bootstrap sampling? So basically Bootstrap sampling has certain attributes. So we'll not go there directly, but let us just assume that Bootstrap sampling does sampling with replacement. So with replacement means that once you pick something from the training set, okay, or from the data set to a training set, you will give that back to the original data. So there will be a chance to select that one more time. So here are some of the Bootstrap. So this is the original data which had only 3 observations, and several Bootstrap samples are being created now. Okay, so you can see that in the first Bootstrap sample, this third observation has been picked multiple times, whereas 2 has not been picked at all. Okay, and there are several properties associated with Bootstrap samples which makes Bootstrap sampling very, very robust. But this is the general idea of Bootstrap. Okay, so when you are using a Bootstrap, some of the advantages are all the classifiers can be trained in parallel. Okay, so it speeds up. Prediction can also happen in parallel. So here we have focused on sampling with replacement. If we don't put it back, so is it sampling without replacement, then it is called as pasting. Okay, so with replacement is bagging, without replacement is pasting. And it turns out that bagging has similar bias with the classifiers but has much lower variance. Okay, and bagging also generates more uncorrelated trees than pasting, because you can understand that as you allow samples to be repeated, that means that there will be more diversity. Okay, all right. So let's now look at some of the other advantages of bagging. So if you pick individual trees, then what will happen is you will see a decision boundary like this, which is linear, but then it is quite convoluted. And when you bag, the decision boundary becomes much more smooth. And not only that, you see that so basically bagging, boosting, random forest, mostly we use decision tree as the base classifier. Now, see what happens is when you use a decision tree, if you remember, the bifurcations it creates are always linear. But in this case, if you see, it has created quite a nice boundary, which you probably get with a SVM's polynomial garden, right? Okay. So there is another concept called as stacking. So basically, stacking also is very, very interesting. So here you have 2 layers of models. Okay, so that's why it calls stacking, right? So you have one layer and then there is another layer. And basically, this came into prominence because of the Netflix challenge that we have discussed earlier. Where there was a $1 million prize to improve the recommendation of Netflix. So essentially what happens is that there is your initial training set on which the base learners are trained. Then that base learners are used to create the predictions. Now whatever predictions they are doing, so these are now treated as features in the next level. And on that you train another model and the final prediction is there. So maybe your name-based predictor is giving a prediction of C1, KNN's prediction is giving a prediction of C2, and C4.5 gives a prediction of C1, and the actual output is C1. So this type of form, this meta learner accepts as a data set and gives the final prediction. Okay. Now there is also one term called as blending, which is used a lot in context to stacking. So essentially, if you look at that, you will see that there is just some difference in terms of how validation set and holdout set is kept aside. Okay. So this stacking is also called as generalizable linear stacking or generalizable linear aggregation. So you can create different meta features, okay, different features apart from the predictions that the learners are presenting. You can take the model parameters, and there are several ways you can aggregate it. So you can get generalized quadratic aggregators, okay, by taking some quadratic features about the model. All right. Okay. So now let's come to boosting. So boosting is also a very interesting process. So whatever we have discussed so far had kind of a parallel characteristics, right? So boosting is completely sequential. So in boosting, what happens is that you build a first level of tree, then you see that where it is going wrong, and it focuses on the errors. Okay. So while it focuses on the errors, it builds another model based on the errors, focusing more on the errors. Okay, so it wants to correct those errors. Again, you focus on the errors, you build another model. So sequentially it happens. So this model is completely dependent on the input this model is producing, and this process is called as boosting. So there are very famous algorithm like gradient boosting, ADA boosting, XGBoost based on boosting, which we will cover in our next class. Okay. So there are also some terms called as random parches and subsamples. So actually, what we are doing so far, we are sampling the rows. Can we sample the columns? So what is the meaning of sampling the columns? So sampling the columns means that we are going to sample the features of the attributes, right? And that's quite interesting concept. So if both the rows and columns are sampled, right, so both the features and the instances are sampled, then it is called as random patching. So the term that is there is called as random patching. And if some of the features are sampled but all training instances are kept, it is called as random subspace. So there is no sampling happening row wise, only by column wise. All right. So now let's go ahead and look at random forest. So okay, so we have discussed about bagging aggregator, which is specialized for decision trees. Okay, now you can understand that bagging trees are correlated, though we are using bootstrap samples. Okay, but they are correlated. So maybe not correlated as it is in pasting, but still correlated. So instead of that, what we can do is, when we are doing the random trees, the thing that we talked about, random subspace, so we'll take different subspace of these features. Okay, so if we have m features, maybe, so we have 100 features, so out of that we'll select 10 randomly, okay, for each of the trees, 10 features out of these 100 features randomly, and then we will find the decision tree using these 10 features, right? So the features this classifier is using and the feature this decision tree is using will be different. So the split they are doing will be different. Okay, so this will generate a highly uncorrelated classifier. So this also tries to trade the variance, bring down the variance, okay, where maybe it will have similar bias or little less bias. So there is also another term called as extremely randomized trees. Okay, so what happens is, when you picked this 10 features, right? So two decision trees, they are taking 10 features each, which are randomly picked. So there is nothing common, and that's why the first split are different for these two trees. Now, what happens in the extreme trees is that you don't look at the most distributive feature. Maybe you find out that which three are my most discriminating feature, and out of them you again randomly pick one of them. So again there will be some kind of randomization which will come into play. Okay, so these are called as extremely randomized trees. And apart from whatever we discussed, another side thing that comes for random forest is that we get a feature importance score. So for each features, so different features are being used for different decision trees. So for each of the decision tree, when a split is being made by that attribute, we look at the reduction in Gini index. Okay, so you remember our discussion of impurity in decision tree. So basically, we just look at that how that particular feature improves the decision tree, and then what we do is we measure it, or we take an average across the trees. So that way we can find out that which feature is more important. Okay. So thank you so much for watching this. As usual, please give your questions in comment section, and I will be more than happy to go through them. And next class will continue with boosting. Thank you so much for watching this video.